Hi, today I am going to discuss about three-phase converters. Last class I have discussed single-phase dual converters that is suitable for high power applications. Three-phase converters are also preferred for high power industrial applications. Today we will see some basic concepts of three-phase half-wave rectifier. Before starting three-phase half-wave converter, I want to discuss the triggering process or how the thyristor turned on in case of three-phase supply. We can understand with the help of this example. Here you can see three diodes are there. In diode number 1, 10 volt supply is connected across to 8 volt and 3 6 volt supply is given. A load resistance is connected. We know that diode will conduct whenever anode voltage is more than the cathode voltage. Now out of these three diodes, there is a confusion that as voltages are more than 0.7 volt, then all the three may conduct, but it's not true. Only diode number 1 will conduct. Let's assume that 6 volt supply turn on diode number 3. Then voltage across cathode of diode number 3 becomes 6 volt. Then all the three cathodes are sorted. So the voltage across all the three diodes cathode voltage becomes 6 volt. Now consider diode number 2. Anode voltage is 8 volt and it is more than 6 volt. So diode 2 will also conduct. Then come to diode number 1. This 10 volt supply is more than 6 volt, so diode number 1 will also conduct. That is not possible. So when diode number 1 conducts, then voltage across the cathode becomes 10 volt, and when 2 conducts it becomes 8 volt, and when 3 conducts cathode voltage becomes 6 volt. So at a time 3 voltages cannot be there at one point. So let's start from diode number 1. When diode number 1 conducts, then voltage across the cathode becomes 10 volt, and across diode number 2, 8 volt supply is less than 10 volt, so diode number 2 will not conduct. Similarly, diode number 3, 6 volt supply is less than 10 volt, so diode number 3 will also not conduct. So ultimately the voltage across the three diodes, though these are positive, but the diode having maximum voltage will conduct. So you can see the waveform that voltage across the resistance is equal to 10 volt and the two diodes are not conducting. That means diode number 2 and diode number 3 remains off. So this principle is used in case of three-phase, half-wave, full-wave converters. That if three thyristors are there, then thyristor having maximum anode to cathode voltage will conduct, and the rest two will remain off. So keeping this one in mind, let's proceed. Let's take an example of this three-phase half-wave converter. Here three AC supply voltages VR, VY and VB is connected across three thyristors T1, T2 and T3. A resistive load is connected as shown in the figure. Let's assume VY is lagging VR by 120 degree and VB is lagging VR by 240 degree. So let's see the waveform. VR, VY, VB are the three-phase supply voltage connected across this converter. Now we can see at 30 degree VR and VY crossing each other, and from 30 to 150 degree VR is more out of these three voltages. From 150 to 270 VY is more compared to VR and VB. Likewise from 270 to again 30 degree VB is more than VR and VY. This 30 degree is equivalent to 390 degree. So we can see for every 120 degree, 30 degree to 150 degree, 150 to 270, 270 to 390. These voltages are maximum. So VR is maximum between 30 to 150, VY is more 150 to 270 and VB between 270 to 390. Now let's consider the case of the diode. As I discussed that out of the three thyristors, voltages are there across each thyristors, but which one is maximum out of these three voltages corresponding thyristor will be turned on. So we can see that between 30 to 150 VR is maximum, so the corresponding thyristor T1 is on. From 150 to 270 thyristor number T2 and 270 to 390 thyristor number T3. Now you can see that in 360 degree there are three output pulses or voltage across the resistance R. So this kind of converter is also known as three-phase, three-pulse converter, and every thyristor conducts for 120 degree. Now let's a load RL is connected across the same system. Three-phase half-controlled converter with RL load. Here at 30 plus alpha, thyristor number 1 is triggered. Though favorable condition is there for thyristor number 1 between 30 to 150, but firing pulse is given at 30 plus alpha. So from 30 plus alpha, this thyristor T1 will be on, and it will continue to be on till next firing pulse is given to thyristor number 2, and it is at 150 plus alpha. Likewise, T2 will continue till 270 plus alpha, and T3 is fired at 270 plus alpha. So the current shifted from T2 to T3 at 270 plus alpha, and this T3 will continue from 270 plus alpha to 390 plus alpha. So here also you can see that three output voltage pulses we have got. So it is a three-phase, three-pulse half-wave converter with RL load. This output voltage can be extended till negative value also if the firing angle is increased or the load impedance is increased. Let's find the average and RMS value of this waveform. As we have got three pulses, so we will analyze only one pulse at a time. You can see from 30 plus alpha to 150 plus alpha, it is single pulse. We will find the average and RMS value in this conduction period, and we will multiply it by 3 to get the RMS and average value. So VR is equal to supply voltage Vm sin theta, Vy Vm sin theta minus 120 degree, Vb Vm sin theta plus 120 degree. Average output voltage equal to 1 by 2 pi integration pi by 6 plus alpha to 5 pi by 6 plus alpha, Vm sin theta d theta, and you will get 3 root 3 by 2 pi Vm cos alpha. You have to multiply it by 3 to get average output voltage of 3 pulses. Then RMS output voltage, likewise we will find that is equal to square root of 1 by 2 pi, then for 3 pulses multiplied by 3, range of integration pi by 6 plus alpha to 5 pi by 6 plus alpha, Vm square sin square theta d theta, root 3 Vm square root of 1 by 6 plus root 3 by 8 pi cos of 2 alpha. So by varying the firing angle alpha, we can vary our average output voltage as well as RMS output voltage. Even from equation number 1, we can say that if firing angle is more than 90 degree, then average output voltage will be negative, and if the firing angle is less than 90 degree, then average output voltage will be positive. Similar case we have seen in single phase converters. So we can say if firing angle is more than 90 degree, then the converter will operate in inversion mode, and if firing angle is less than 90 degree, then it will operate in rectification mode. So today I have discussed just the basics of three-phase half-wave converter. We have seen that though favorable condition is there for all the three thyristors, but only one thyristor will conduct which has maximum anode to cathode voltage out of those three phase voltages. available across the three thyristors. Then we have found out the average value and RMS value of the converter. In coming classes, we will see three-phase full wave converter. Thank you.